composed of closely spaced orbitals. Solids can be either metals or materials, and they are broadly classified into insulators, semiconductors, and conductors. Insulators, semiconductors, and conductors. This classification is based on energy band, energy gap between valence band and conduction band. So you can clearly observe here. This is the valence shell electrons, valence orbitals. These are the conduction orbitals. Whenever they are entering into the excited state, whenever they are absorbing energy. Suppose this gap between valence band and conduction band is more, large energy gap is there, it requires more energy to enter valence electron from valence band to conduction band. It requires much energy due to large energy gap in between these two. Hence, these are known as insulators. Here you can observe in semiconductors, there is a small energy gap in between valence band and conduction band. Valence band and conduction band. So if we are heating thermally or electrically or doping, we can easily, our electron can easily enter from valence band to conduction band. Hence, these are known as semiconductors. These are known as semiconductors. Here, in the conductors, there is no gap. There is no energy gap in between valence band and conduction band. So, these are overlapped. These two bands are overlapped with each other. Hence, conductors can conduct easily because valence electrons from valence band can easily enter into the conduction band. Hence, these can act as a good conductors. Wherever energy gap is very less or there is no gap, these two bands may be overlapped, that material are known as, or that metals are known as, that solids are known as conductors. Where the energy gap is less when compared to or in between insulators and conductors. Energy gap is in between, less than insulators, more than conductors. These are known as semiconductors. Energy gap is very large, they are conductors. As per energy gap in between valence band and conduction band, solids are broadly divided into insulators, semiconductors, and conductors. Insulators have large energy gap. Large energy gap or forbidden gap. Forbidden gap in the sense, same from here to electrons, if this has to enter, it has to conduct electricity or heat, these electrons has to enter from here to here. It requires much energy. So energy gap between valence band and conduction band having large. Hence, they do not allow heat or electricity to pass through them. So most of the organic and inorganic solids except graphite are categorized under insulators. Graphite is different. Due to layer structure, it can conduct the electricity. Semiconductors or materials have less energy gap when compared to insulators and little more energy gap when compared to conductors. Therefore, at normal temperature, thermal or electrical conductivity of these materials lies between insulators and conductors. Example, silicon and germanium. Best example is silicon and germanium. Best example is silicon and germanium. Next, conductors. The energy gap of these materials is overlapped between valence band and conduction band. Therefore, they can conduct of electricity and heat. Example, majority of the metals. Majority of the metals. So, metal plays important role. Along with that, semiconductors having lot of importance. At room temperature, semiconductors allow a portion of electric current to flow through them. But the electrical conductivity of a semiconductor at normal temperature lies between that of a good conductor and an insulator in the range of 10 to the power of minus 9 to 10 square. Ohm inverse, centimeter inverse. At normal temperature or room temperature. But semiconductors, which are perfect insulators at absolute zero. Semiconductors are those solids which are perfect insulators at absolute zero but conduct electric current at room temperature. At absolute zero, semiconductors act as a perfect insulators. But at room temperature may varies. Suppose in sometimes 28 or sometimes 32, 35, peak summer 45 too. But these conducts at room temperature. Silicon and germanium. These two are very important elements used as a semiconductors. The pure samples of these elements are obtained by John refining. Some impurity is added deliberately to these elements by a process called doping. What is meant by doping? Addition of some other material like boron or aluminum to silicon and germanium. These are act as a good conductors. But actually silicon and germanium is a semiconductor. Due to doping, their conducting capacity will be enhanced. Actually, semiconductors are two types, intrinsic semiconductors and then extrinsic semiconductors. Intrinsic semiconductors also known as, these act as, intrinsic semiconductors act as a conductor due to thermal defects. Pure silicon or germanium act as an insulator because electrons are fixed in a covalent bonds and are not available for conduction at room temperature. But at high temperatures, electrons are released by breaking off some of the covalent bonds. These electrons move freely in the crystal and can conduct electricity. Actually, at absolute zero temperatures, they are insulators. But whenever temperature rises, covalent bonds can easily break up, and whenever covalent bond is break up, free electrons are moved from one place to another place in crystal. Hence, they show electrical conductivity. They pass conductivity. They conduct electricity without introducing an external substance. These materials show conduction. Hence, these materials are known as intrinsic semiconductors. Intrinsic, within that, due to breaking of covalent bonds with the temperature. Then, what is the effect of doping on conductivity and band gap? Then, extrinsic semiconductors. Semiconductors due to impurity or semiconductors due to doping. Silicon and germanium are group 14 elements. So these are in the carbon family. So carbon having electronic configuration NS2, NP, NS2, NP2. Same thing in silicon also. So carbon atomic number is 16, right? So 1s2, 2s2, 2p2. Sorry, carbon atomic number is 6, right? So 1s2, 2s2, 2p2. Outer electronic configuration is 2s2, 2p2. And then that group is the NS2, NP2 electronic configuration. Silicon, germanium also. In the silicon and germanium, so these are also group 14 elements in pure state have very low electrical conductivity. If the low electrical conductivity of these elements is greatly enhanced by addition of even traces of an elements belonging to group 13 or group 15. Group 13 is the boron family. Group 15 is the boron. Yeah. 15 to the group 14 elements, that is silicon or germanium. The induction of group 15 and group 13 elements to crystal lattice of group 14, silicon or germanium, produces N or P type semiconductors. N or P type semiconductors. So from the group 13, aluminum may add. In group 15, phosphorus or arsenic may add. Suppose, depends on the addition of impurity, these extrinsic semiconductors are further divided into N-type semiconductors, P-type semiconductors. N-type semiconductors, N stands for negative here. So this type of semiconductors is produced due to metal excess defect. So metal excess defect in the sense, so in the, crystal defects, right? Actually in the crystal formation, in the lattice formation, in anywhere, actually in regular period, atoms are arranged, metals are arranged. In anywhere, any atom is in the internal space with excess atom is present, excess metal is there. So that is known as metal excess defect. Or by the addition of trace amount of group 15 elements like phosphorus or arsenic to extremely pure germanium or silicon. Pure germanium or silicon. Actually, germanium or silicon outer cell I mean NS2, NP2, 4 electrons are there. But if we are adding phosphorus or arsenic, what is happening? Either phosphorus or arsenic in outer cell, NS2, NP3. 5 electrons are there. 1 electron is excess. 1 electron is excess. This 1 electron from the phosphorus or arsenic, they can move in between the in solids from one place to another place. Freely, these electrons will be moved. With this, I mean moving of electrons having negative energy, hence these are known as N-type semiconductors. Even metal excess defect also with excess electrons. At the same time, by adding up 15th group elements like phosphorus or arsenic also, actually silicon or germanium having in the outer cell only 4 electrons, but phosphorus and arsenic having 5 electrons. While we are doping, this 1 electron from each atom is excess. These electrons move within the space of crystal lattice. They can, with that movement of electrons, conductivity will be tremendously increasing. Conductivity will be increasing tremendously. These type of conductors are known as N-type semiconductors. P-type semiconductors. P-type semiconductors, these type of semiconductors are formed due to metal deficiency defect or by the addition of impurity atoms containing less electrons. I mean 13th group elements like gallium, indium, for silicon and germanium. Whenever we are adding 13 group elements like gallium or indium, they having in their outer cell 3 electrons only. But silicon and germanium having 4 electrons. Here, 1 electron is less. Less electron is known as positive hole. That's why these are known as the P-type semiconductor. P stands for positive, electron deficiency. Electron deficiency. So you can easily understand what is the metal excess and then what is the metal defects. Suppose this is the crystal lattice. I mean, this is extra negative ion is there in between the here. So metal excess defect here, this is the, I mean, lattice of any crystal, any solid. Suppose here A plus B, 2 elements are there, 2 atoms are present here, one positive, one negative. But here, one negative, B minus is lost. Loss of negative ion in the crystal lattice. Due to that, here, one excess electron is added. Hence, this is a metal excess defect. But here, positive ion. Excess positive ion is reached here in between the internal interstitial position of the lattice. Interstitial position of the lattice. This is extra positive ion is there. If it is extra positive ion is there, mean extra electron is there somewhere to compensate the energy. So metal deficiency defects, Here somewhere, so here there is no positive ion, atom. So this is the metal deficiency. Or somewhere it is, so here it is not there, but in here two ions are there. Due to that also, electric movement will be, conduction will be observed. Due to that, P-type and then N-type semiconductors. So P-type semiconductors, N-type semiconductors are formed due to metal excess defect. If metal excess is there, somewhere extra electron is there in the interstitial position of the lattice. Then, or otherwise, if we are doping group 15 elements. At the same time, P-type semiconductors are formed due to metal deficiency defects. Here electrons are, positive hole is formed. Or otherwise, we are adding group 13 elements like boron, gallium, indium. These are known as P-type semiconductors. Broadly, semiconductors are classified into intrinsic semiconductors, that is due to the thermal defects. Then another one is the extrinsic semiconductors. These are due to doping or impurity. Extrinsic semiconductors are further divided into N-type semiconductors and then P-type semiconductors. Which one we are adding or doping? Either 13 group, if we are doping, P-type semiconductors are formed. If we are doping 15 group elements, N-type semiconductors are formed. Then what are the applications of semiconductors? Semiconductors having lot of importance depending on the nature of the impurity. These are used in transistors to expose metal as a photoelectric effects. Nowadays, photovoltaics, due to that, we are using many things. Solar photovoltaics, anywhere we are using semiconductors. A combination of P and N type of semiconductors used as a PN junction, diodes. Electric current from outside to flow through it one direction. These are known as PN junction or rectifier and is used for converting alternating current to direct current. So there is a lot of important applications are there. Here semiconductors also elements of group 14 silicon and germanium and group 15 phosphorus, arsenic, strontium. Elements of group 13 and 14, these are the N-type semiconductors. These are the P-type semiconductors, boron and gallium, indium with silicon and germanium. Then elements of group 13 and group 15. These are also plays vital role. Elements of group 12 and group 16 like zinc sulfide, cadmium sulfide, cadmium selenium. All these various semiconductors nowadays we are preparing up to nanoscale, nano size, having lot of importance as a semiconductors as a transistors or photovoltaics or solar cells, solar photovoltaics or PN junction diodes, like that in various stages. Next we are going to superconductors. Semiconductors actually normal temperatures, silicon and germanium is the act as a semiconductors, but at absolute zero they are act as a insulators. But what is the difference between semiconductors and superconductors? Superconductors, in the superconductors, the electrical resistance of a metal depends on the temperature. The electrical resistance decreases with decrease in temperature. See, superconductors. Actually, in semiconductors, if it is increase the temperature up to certain level, conductivity will be increased. But here, electrical resistance decreases with decrease in temperature and becomes almost zero nearer the absolute temperature. Here I am explaining electrical resistance. In superconductors, electrical resistance at absolute temperature or near the absolute temperature, absolute zero, is almost zero. Materials in this state are said to possess superconductivity. So superconductors can conduct the electricity at absolute zero temperature also, due to decreasing of electrical resistance. Hence, superconductivity may be defined as a phenomenon in which metals, alloys, and chemical compounds become perfect conductors with zero resistivity at temperature approaching absolute zero is known as superconductivity. So once again I am repeating, superconductivity is a phenomenon in which metals or alloys or chemical compounds become perfect conductors with zero resistivity at temperature approaching absolute zero. Superconductors are diamagnetic. The phenomena was first discovered by Ons, Commer Link Ons, in 1913, when he found that mercury becomes superconductor at 4 Kelvin. The temperature at which the substance behaves as a superconductor is called transition temperature. At which temperature substances behave a superconductor is called as a transition temperature. Most metals exhibit this phenomena at temperature range 2 to 5 kelvins. 2 to 5 Kelvin. But many efforts are being made to find materials that behave as a superconductors at room temperature, because attaining low temperature with liquid helium is highly, maintaining low temperature is difficult, highly expensive, economically not viable. Hence, the at highest temperature which superconductivity has been observed is 23 Kelvin for alloys niobium and germanium. Alloys of niobium, that is Nb3 germanium. Since 1987, many complex metal oxides have been found to possess superconductivity at fairly high temperatures. Example, yttrium, barium, copper oxide. Why? Ba2Cu3O7 at 90 kelvins. Bi2Ca2 Sr2Cu3O10 at 105 Kelvin. More than room temperature. And then tantalum, Tl2, Ca2, calcium, barium, Cu3, copper 3, and then O10, 125 kelvins. So these having many applications in electronics, building magnets, aviation transportation, power transmissions, various examples. So these are conductors and superconductors and their applications. depends on the conductivity at various